In this example, we have objects that are going to be connected via a pulley at a right angle. So it's really important that we get the free body diagram right so that we can make assumptions about some of the information that we have. So if we draw a quick sketch first, we're going to have our pulley here, and we have our cart. Might look something like this. Our cart is going to be on wheels. And then your rope will look something like this, going over the pulley and then attached to some mass hanging below. So given this picture, we know that we have Fn. We're going to have some sort of Ft going towards the pulley from the cart, and of course Fg. And then what our mass has is some other Fg, so we'll say Fg2, and then your Ft again. So in general, our motion is in this direction. We know that this is our M1 is the cart, M2 is our hanging mass. So we have M1 is equal to 1.50 kilograms, M2 0.700 kilograms. We are unsure of the acceleration of the cart, and we are unsure of the force of tension at this point. And we know G 9.8 newtons per kilogram, or meters per second squared. So let's take a look. Let's redraw our free body diagrams, and we're going to redraw them just in the X and Y direction, just to make our lives a little bit easier. So we have our free body diagram of the cart, also known as M1. This is a frictionless surface, so there's nothing going backwards. So we have Ft, Fn, and Fg1. Now take a look at mass 2. Again, we're just drawing everything as if it's in the XY reference, or just an X reference frame. For M2, we would have Fg2, and of course Ft, intentionally opposite to the Ft in the first diagram. And our net kind of looks like this, simply being pulled by Fg2 and mass 1 plus mass 2. Because again, there's no friction pulling it backwards, right? So the cart is moving in that direction, in the right and then down direction, being pulled by its masses, which are simply a function of the sum of the mass and then gravity. So this is what our diagrams will look like. So I've left my free body diagrams on the screen here as we go ahead and try to solve some of this. So we know, of course, Fnet, start as we always do, is equal to MA. And MA is M total. So M total is simply going to be M1 plus M2 times acceleration. And given our diagram, so we're looking here at this free body diagram, that is simply going to be equal to Fg2. Fg2 is going to be equal to M2 times the acceleration due to gravity. And now given all this information, we can start to substitute values in and rearrange. So we have an M1 of 1.50 plus an M2 of 0.700 times our acceleration, which we still don't know, but that we're going to be solving for. M2 is 0.700 times your force of gravity. Okay. Given the way we've drawn our diagram, I've taken care of any negative signs that have to relate to directionality here. So I can simplify and rearrange. That's going to give me 6.86, and that's newtons, over 2.2 kilograms, which are the correct units for acceleration. And that leaves us with 3.1 meters per second squared. Now, being able to interpret this answer is very important. This is going to be in the same direction as F2, which is to the right in our free body diagram, which means translate that to our original picture, F2 is going down, right? So if we remember from our original picture, we had the cart, and then FG2, sorry, was down this way. So since FG2 is pointing down that way, since A and FG2 are in the same direction, we can conclude that this is in the down direction. The second part of this question asks us to determine the tension in the cable, so that's Ft. So we're going to start looking at where we incorporate Ft into our equation. So let's start off as we normally do with F net, and that is equal to Ma. And in this case, if we take a look at which of our free body diagrams includes some value of m, anything else we know, which in this case we know Fg2, and Ft, well, we're left with this diagram highlighted in yellow. So what that really means for us is that it's no longer Ma, it's M2A. And what's that equal to? Well, that's equal to Fg2 minus Ft, because of course they're in opposite directions, right? So we can rearrange this and solve for Ft. Ft is equal to Fg2 minus M2A. And then by substituting everything we know, we'll be able to solve for the tension in the rope. So we're left with 0.700 kilograms times the acceleration due to gravity, 9.8 newtons per kilogram, minus 0.700 kilograms again, times the acceleration, which we previously solved, 3.1 meters per second squared. That's going to be equal to 4.7 newtons. Now take a look at our diagram. Ft is pointing in the left direction, which given our images from the first slide means that it's going up. So this means that Ft is in the up direction.